Hello, good afternoon, good morning, good evening, maybe somewhere. Thank you, everybody, for your attendance to this webinar. I'm going to make a very short introduction just before going to the matter of the webinar itself. As you probably already know, this webinar is about a very specific topic that is to present and discuss with you in a little more than 1 hour, approximately, the results on this comparison exercise on neutron spectra unfolding in Bonner sphere spectrometry that we organized within the activities of EURADOS during the last years. This has been an exercise or a comparison exercise that has been organized in collaboration among these 5 institutions, with the participation of in the organization of myself, together with 5 other colleagues. And now in this webinar, we will have 3 presentations, approximately 15-20 minutes every one. This 3 presentation, after finishing this welcome to all of you, will be first a brief overview of this EURADOS exercise that will be presented by myself, an analysis of the EURADOS, the solutions submitted for this exercise that will be presented immediately after by Carles Domingo from the University Autónoma of Barcelona in Spain. Finally, we will have a last presentation by Roberto Bedoni from INFM in Italy, with some practical recommendations for PSS and FAR. And at the end, we will have some time for discussion. I think it's important to, this is all the results and also the details on this exercise has been already published. The first paper, published in Radiation Protection Dosimetry some years ago, is a description of the exercise. And I think even more useful for all of you could be the second paper that has been published a few weeks ago in Radiation Measurements, discussing the results and containing also all the material for this exercise. So this is an open source paper that you can download. You can also download as supplementary material all the specification for the exercise. So I think this second paper could be useful for all of you in case you are interested in Bonner sphere neutron unfolding. As you can imagine, the purpose of this webinar is not to teach you about completely about unfolding, because this is a very complex problem. This is just to discuss the results and the consequences of this exercise that we organized within the EURADOS activities. So now we are going to continue with the first presentation. This will be made by myself, and it is to provide you an overview of the exercise that we organized. As probably you already know, what is the Bonner sphere spectrometry and the unfolding problem? Well, this is a system that has been used for many years for measuring neutron spectrum. This is quite well described, for instance, in these references you can see at the bottom of the slide, among other, some others. And it is based on a very, in principle, simple idea, but with some tricky issues that need to be considered. We put, or we have a thermal neutron detector at the center of different moderating spheres. We can calculate what is the response as a function of energy. If we have these response functions for the different spheres, actually we have a response matrix. So in terms of an integral, the counts measuring or measured with every sphere can be expressed as the folding of the response matrix with the fluence spectrum. When we have a given energy binning, this integral is replaced by a summation, not an integral. And the unfolding process is actually the inverse mathematical operation. I mean, we know what is the response matrix. We know what are the set of counts measured with every sphere, and we need to obtain the neutron spectrum with a given energy binning corresponding to the response matrix we are using in this case. Obviously, this unfolding problem is underdetermined problem. So it means that there is, from a strictly or only mathematical point, there are infinite mathematically possible solutions, all of them correct from a mathematical point of view. This arises from the situation that the number of spheres, I mean the number of equations, is usually much lower than the number of energy groups. This is the number of variables. So the only way to solve or to deal with these problems depends on the approach we are using for the unfolding. When the spectrum is modeled as a function of physical parameters, this is we can refer it as a parametric approximation. It is necessary to provide the unfolding process with initial guess values, and this initial guess needs to be close to the actual values, because otherwise the solution will converge to incorrect values. When the spectrum is modeled as several energy groups, it's necessary a guess spectrum. This guess spectrum will be perturbed during the unfolding process, just looking to converge to the spectrum we are looking for. And again, it will be necessary to start with a guess spectrum as accurate as possible, because otherwise the convergence could be to a non-physical spectrum that mathematically is one of the solutions of the problem, but could not correspond to the physical problem we are trying to solve. In this case, the idea of this exercise was to provide to the participant or the people interested in solving the problem one set of counts for different scenarios and ask them to use their own codes to solve the unfolding problems. We decided to use not a physical boundary spheres spectrometer, but an idealized one. This one consisted, as you can see, just a very simple helium-3 thermal neutron detector inside a set of spheres that include from 2 inches diameter till 12 inches diameter. And the response of the detector was calculated using Monte Carlo simulation as the number of neutron reaction in the helium-3 inside the detector. These are the 4 scenarios that was considered for the exercise. We consider first LINAC, medical LINAC, actually a Saturn LINAC, 25 megavolts energy situated at the center of a bunker or a treatment room. And we consider 2 points, one at 1 meter from the isocenter and the other at the entrance of the maze. We also consider a workplace field consisting of an americium beryllium source with this geometry that is depicted in the figure. The third scenario was an irradiation room consisted on americium beryllium source at the center of an iron sphere and a measurement point that was 4 meter distance along one diagonal. And the fourth scenario was a sky-shine problem with an alpha neutron source in the center inside a cylindrical room, and the measurement point was located at 100 meters of distance. For every of these 4 scenarios, we calculated directly what was the number of counts for the different spheres. It's important to emphasize that these counts were directly calculated, not by folding the spectrum with the response matrix. So we tried to simulate what was or what should be the physical measurement process. In addition, we perturbate the calculated counts via uncertainty that was typical from the problem we were considering: LINAC, workplace, radiation room, and SkyShine. This will be discussed more in detail in the next two presentations. We provided the participants with this, with the response matrix of our idealized Bonner sphere spectrometer. We provided also this set of counts for the 4 scenarios that were actually 5 sets of counts, because there were 2 points of measurement in the case of LINAC, and we asked the participant to unfold the spectrum. Then the idea was to compare the unfolded spectrum with the true one or the reference one to identify the discrepancies and to investigate what we can learn for this from this exercise and comparison. This is the unfolded spectra compared with the reference. Actually, obviously when the participant made this calculation, and when we made this calculation, we made it without knowing the reference solution, because this is the case, the real case. And as you can see, when the unfolding codes, independently of the code, is used properly, usually the spectrum can be obtained with a good accuracy. Only in case of a very detailed structure, depending on the case, sometimes cannot be identified if they are very thin resonances. But the spectrum can be obtained very accurately in all the cases. There is only one thing that maybe it's interesting to mention, is that if we plot the case of the LINAC more in detail, one of the things that we can see is that in all the cases, the unfolded spectrum for point 2, which is the point that is at 1 meter from the isocenter, the solution practically is very accurate in all the cases. But for the point 1, which is at the entrance of the maze, there are some discrepancies, in particular for the fast and the epidermal part of the spectrum. We found this small discrepancy in all the cases, both for parametric unfolding and also for spectrum unfolding using accurate guess spectrum. This can be realized in the figure you can see on the right side, because there are some discrepancy, in particular when we compare the counts and the folding of the spectrum with the response matrix in this region corresponding to the intermediate spheres of the Bonner sphere spectrometer. This is due to the perturbation of the field that it is caused by the Bonner spheres. So this is not a problem with the unfolding, but it's with the condition the spectrometer is used. There are some requirements to use properly or to use accurately the Bonner sphere spectrometer, and one of them is that the fluence should be more or less constant over the volume of the sphere, and the other is that the presence of the sphere should not perturbate the neutron field we want to measure. When the sphere is very close to one wall, there is this perturbation, because without the Bonner spheres, we have 3 contributions, schematically indicated on the left, but when the sphere is located on the position, the contribution to the response are not exactly the same. So there are some perturbations that were introduced when the sphere is close to the wall, but not when the sphere is far from the wall. And actually, this perturbation affects mainly to the intermediate volumes, because when the sphere is very small, the perturbation is not relevant, and when the sphere is very big, the perturbation is relevant, but it affects mainly to the thermal neutrons, and big spheres are not sensitive to thermal neutrons. We checked this just with Monte Carlo simulation. What we realized is that effectively this discrepancy for the point located at the entrance of the maze was due to the perturbation of the field caused by the war. This is mainly an academic question. Maybe academic is not the right adjective, but what I mean is that this discrepancy, as you can see, is in the order of 4 or 5%. This is relevant for metrology, obviously, but in this case that we are not talking about a metrological application, because in this case it's just measuring the field surrounding a LINAC. 4% of discrepancy is an uncertainty that can be accepted. This is just one thing that can be seen is that if we mathematically or using Monte Carlo simulation, we remove this perturbation from the count, well, in this case, the unfolding just using or just considering the unperturbed field can be obtained or can be solved accurately, both in case of 0.2 as well as in case of 0.1. Well, in summary, what is just before going to the discussion of the result of the exercise that I think is the most interesting part of this webinar is, first one is that Bonner sphere, the unfolding with Bonner sphere spectrometer is an undetermined problem, so it's essential to have additional information to get a physically meaningful solution, because otherwise there are infinite possible mathematical solutions. There are some checking that it is necessary to do because there are some necessary but not not sufficient conditions that can be performed with the solution. One very simple is just to fold the response matrix with the unfolded spectrum, and we should obtain the counts we measured previously. Additional checking should be done just to check or to have more guarantee that the solution is correct. And finally, there is one advertisement that I think is this is something that I remember one colleague that now is retired, but he used to say some years ago is Gianfranco Gualdrini used to say that amazing result used to be incorrect or inaccurate result. This is practically not only for unfolding, but also for simulation, for many problems or experiment. When you find something which is very strange, perhaps you discover something amazing, but in most of the cases, it means that something were not made in the correct way. If you are interested in obtaining more information, the first reference discuss in details the exercise, in particularly all these things I mentioned about the perturbation of the field and so on. So I think it's could be interested to have more information about how the exercise was proposed. And the second one is an exhaustive and complete discussion about the result and contain itself as additional material this exercise, so you can perform it by yourself in case you didn't participate in this exercise. So from my part, we are going to continue with the second presentation. If you think we thought that it would be better to have the three presentations together, one after the other, and at the end start the discussion at the end of the three presentations instead of mixing the question with the presentation. So we will continue with the next presentation.
Okay, thank you very much, Jose Maria. I am now presenting the results of the exercise, and I have to say that I am going to present a summary of what it is already published in the papers that Jose Maria just told you. And I have to say that, there are many things and many details that can be somehow extracted from these results. Uh, we have only time to give a general overview of them. And I think that the most important thing from these results is that there are several lessons to be learned on how to treat the results of an unfolding process. Maybe let me start from one of these conclusions that everybody who's using unfolding should be aware beforehand is that unfolding cannot be used as a black box. I mean, results have always to be analyzed afterwards. And we'll see that some lessons and some particular aspects uh, can be somehow extracted from the results of this exercise. So, first of all, let me give a summary of the participants. There have been 20 participants from 15 countries, and we want to keep, I mean, we want to keep the users not known, so just the general list of them. And I am not going to give not even hints from the countries that the participants come from. I am just going to say that we have grouped the results as a function of the different unfolding codes that have been used. There are mainly two groups of unfolding programs that have been used in the exercise. One of them being the well-known Maxet and Gravel unfolding codes packed together in the UMG package, which is all this group here. And there is also a smaller group using the Fruit unfolding codes. This in addition with some particular participants who have used self-developed or specifically made unfolding codes for the information for be used in the exercise. I have to say that not all the participants gave all the information about which kind of pre-information they used. As Jose Maria told just a few minutes before, there are basically two ways to give the pre-information to the unfolding. One of them is using a parametric approach, fixing some of the parameters that define the spectrum in, let's say, a physically relevant way. And there's the approach of making, let's say, more mathematical operations, trying to minimize the dispersion between the accepted spectrum and the counts of the spectrometer. Um, uh, for doing that, we need to start from a gas spectrum. And I have to stress that the results of the unfolding depend very much on how good the starting spectrum, the gas spectrum, is. So basically, Fruit allows using the parametric mode, other codes also. And basically, Maxet and Gravel need gas spectrum to start the unfolding. So now we know what participants have, in which of the exercises the participants have participated. Not all have participated in all problems. And here we have a list of how they manage the pre-information. So let's start from the solutions of the LINAC problem for point one. Point one is that point which is closer to the maze, so where there could be some problem related with, neutrons just being thermalized and being more affected by the wall structure of the room. So here we can see all the solutions provided by the participants. And we see that the first group of participants, which use the parametric approach, these participants here, they all say that we're using a parametric approach. Okay, the aspect of their solution is a little bit different than the reference one in the high energy, in the evaporation energy region of the spectrum. And okay, you can see all these details, and here we see one of the participants which gets the peaks out of the energy. And here in this set of participants there, we see a spectra which are quite different than the reference one. Okay, just analyzing this from the point of view of watching the spectra, one should think that the resulting spectra should be physically meaningful. Okay, there we have a evaporation peak that could be physically relevant. Okay, the energy of the evaporation peak is wrong, but okay, from the aspect of the spectrum, maybe this solution cannot, should not be eliminated beforehand. But for sure, if we fault this spectrum with the response functions of our spectrometer, for sure it does not reproduce the sphere counts that were given to the participants. Something similar happens here, but here, probably the participants should suspect that there was something wrong in the thermal peak, as, okay, it doesn't seem physical to think that, okay, a so broad thermal peak going up to temperatures so high. The thermal peak is in equilibrium with the room temperature, so energies of the thermal peak have to agree with the thermal equilibrium in the room. Now, another point which is quite significant is that for this point, when we compare the fluence in the different energy groups that the participants were providing, it looks quite similar to the reference values. Okay, there are fluctuations, there are maybe some small differences, but okay, this graph does not look bad. But if we see the graph of the ambient dose equivalent values obtained from the fluence, then we see that almost all participants were low in the almost all the participants were low with the value they found. So there's some systematic mistake here, in the sense that probably a small difference in the fluence fractions, as were seen here for the high energy, then probably are affecting very much to these H star 10 values. Same happens for the fluence average energy and the H star average energy because of these small variations in fluence. So unfolding tide tends to give right resource influence, but small differences in the how this fluence is distributed in energy give big differences in other integral quantities of the spectrum. Now, let me go faster for the other points. Point 2, the agreement is a little bit better than in point 1. The same users have spectra which are different than the reference ones, and again the same behavior here, but here the results for ambient dose equivalent are more fluctuating around the right level. So probably point 1 is, point 2, which is closer to the isocenter of the LINAC, was better treated by the unfolding process. So we go to the simulated workplace field, and here we see that again in the users that, these users here were again out of the reference spectrum. And okay, the other ones, there are some solutions here clearly divergent from the reference one. Okay, so let me just continue and make clear that probably these spectra which are outside, the users should have realized that they were outside if they had folded the solutions to see if they reproduce the counts. So nothing else new to be said in this slide, just presentation of the values. Again, this problem seems in general to have a good approach. In fact, this was one of the problems where more information was available. Now, next problem, calibration facility. Here we see in the middle spectra and the top right spectra that they quite agree with the reference spectrum. And this is probably due because the information that was given in this problem was sufficient to make a very accurate simulation. So a good starting spectrum was found by many of the participants, and then the unfolding process was quite straightforward. Now in the top left figure, we see that the users who used the parametric approach for the evaporation peak, the total area below the peak more or less may be the same as the reference one, but it is distributed differently. The peak is narrower and higher. And this is probably because the parametric approach was not sufficiently flexible to let the spectrum change sufficiently to fit the reference one. So when parametric solutions or when parametric approach is used, we have to leave the parametric spectrum with sufficient degrees of freedom to for the spectrum to be similar to the reference one. Again, in the bottom figures, there are strange results. Simply the M spectrum is wrong. And then again, the same problem with the white thermal peaks in the bottom right figure. So going again for the integral quantities, again here, small differences in the fluence distribution here overestimate a little bit the ambient dose equivalent rates. Another thing is that the uncertainties that are presented in these figures are those provided by the participants. Maybe they are somehow underestimated. So if uncertainties provided by the participants were bigger, probably more of the values would be compatible with the reference solutions. So not many detail was said by the participants on how uncertainties were calculated, so we cannot analyze where is exactly the origin for these discrepancies. Finally, the sky shine problem, where there were less participants that participated in solving this problem. And here is where we have some of the most, I would say, strange spectra obtained as a solution. The figures in the middle and the top right figure, they come from gas spectra and unfolding, just minimizing the mathematical function that we are getting. And in almost all of them, there's a kind of double thermal peak, which is completely unphysical. There is no physical reason why neutrons of this energy, higher than the thermal, could accumulate in there. So this is an artifact that sometimes numerical unfolding methods do. Mathematically, they find a better solution, but as it was said at the beginning, the number of mathematically acceptable solutions is infinite. Which of them have physical sense, that has to be decided by the person who uses the unfolding program. And in this case, I am also sure that folding the spectra with the response functions will not give sphere counts compatible with the measured ones. So this is a check that, as far as we know, no participant has made in the exercise. Nothing else to say about spectra which are out of the reference ones. Okay. So again here, maybe this is the exercise where the agreement with the H star and energy average is maybe worse than the other ones. So from my part, I think that there is nothing else to be said other than analyzing the results, and maybe in Roberto's talk we will hear about some of the precautions that should be taken after having the results. So thanks very much, and now I pass the floor to next speaker, to Roberto Bedoye.
Good morning, good afternoon to everyone. My name is Roberto Bedogni. I thank Carlos and Jose Maria for the previous talk. They mentioned already a number of practical recommendations, or they evidenced a number of points where by using some recommendation or some experience-based trick, the process could have performed in more accurate way. So my task is now made easier because you have mentioned many things already. So in addition to putting these tricks together in a list and mentioning them one by one, I will try to give some simple practical example, especially about the topic of pre-information. And of course, I would like to thank EURADOS for this webinar, this opportunity. So when starting with the Born sphere problem, the user should always look at the counts profile. There are codes there put the plot profile in a place where you can continuously look at it and see whether there are strange features. The experimental count profile should obey to some common sense rule. Common sense, if you think to how the response functions of the spheres are the shape of the response function of the different Born spheres that are continuous functions. So the curves, the plot profile curves should be smooth if the measurements are taken under stable condition using the right monitors and are not affected by supplementary uncertainty of unexplained origin. This was said by the historical references like the one from Alevra and Thomas, 2003 radiation protection dosimetry. What does it mean? You know that, for example, sometimes when we perform a measurement in particle accelerators, we cannot rely on the stability of the source as if we were in front of a radionuclide source. In particle accelerators, we need a beam monitor, and sometimes the beam monitors that we may use or that we may propose for the experiment can be affected by bias. For example, they can be affected by nonlinearity, and when this happens, there is a bias in the data. Or sometimes something can be wrong with the detector. Maybe there's a problem in the cable or in the electronics, giving rise to spurious pulses, and possibly there may be extra counts due to some electronic noise or electromagnetic interference. So an example evident in this exercise could be the skyshine problem, not possibly because of a not right monitor, but possibly a measurement problem. Imagine a skyshine measurement where you are assuming some hypothesis possibly the facilities is maybe an accelerator-based facility, and again you have the monitor problem. Or maybe because the sky-shine flux is not is expected to be very low in intensity, you have to expose your spheres for hours and hours, and maybe during these hours and hours there may be some problem in the counting electronic, or maybe the detector can slightly move from the original position, or may slightly move from the center of the sphere, giving rise possibly to problems like the one evidenced here, also by the red arrow. In this case, in a real experiment, we should think to repeat the measurement, to perform some further investigation. In a simulated experiment like this one, the user could decide to exclude this point from the set of data used for unfolding, as this point could lead to bias the result. So then, after checking the sorry, I don't know what is going on with my presentation. I can't see anymore my presentation. Okay. After checking the count profile and verifying that there are no unexpected deviations due to systematic facts, the participant should start thinking how to prepare, how to assemble the pre-information. We observed and previous presenters said it, that more deviating resulting spectra were obtained in scenarios with less specified scenarios, or a scenario where the pre-information given to the user was lower, namely the LINAC problem or the sky-shine problem, where 40 or 70% of the solution were significantly deviating from the reference solutions. But even for the simple cases of the radiation field and the workplace field, there were a significant number of deviating solutions in the order of 30% of more or more of that. So preparing the pre-information is very important because, as it was said already, there are infinite mathematical functions that we could call spectrum or spectra that could satisfy the problem in a mathematical sense, meaning that there are infinite functions that, folded with the response matrix, could reproduce the counts that we want to unfold. So to orient the unfolding code, or to guide the unfolding code toward a physically meaningful set of solutions, then of course this set cannot be a point because there are uncertainties. So this set of acceptable solutions, according to the uncertainties involved in the process, will not be a point, but a set more or less large, with a larger or smaller radius in the space of the solutions, according to the uncertainties, to the uncertainty budget. So what does it mean preparing or assembling a physically meaningful pre-information? If you are using a parametric approach, you should select the right model, or if, because it is always known if we are in a nuclear reactor, if we are in a radionuclide source, if we are in a particle accelerator, should there are means to know which physical model to produce neutron spectra is the most suited one. And if we are using parametric approach, also the initial estimations of the parameters is important. If the unfolding code is based on altering a gas spectrum according to some mathematical convergence algorithm, a steepest descent, a special gradient, or a maximum entropy, or other, then we should make sure to provide a plausible gas spectrum. Generic but always valid recommendation is please try to take into account in the pre-information any pre-information you have. I make an example. If you are unfolding a radionuclide source where you use the shadow cone, then you are sure that the final spectrum should not include thermal neutrons. So you could impose 0 thermal neutrons in the unfolding problem. If you know the minimum or maximum energy, you should put, again, a cut in the energy domain, just to make examples. I will make a practical example, just to show you which result can be achieved if we assemble in different ways the pre-information. Using a parametric approach to describe the irradiation room problem, okay, where the source was an americium beryllium source, which spectrum was degraded in an iron sphere. Suppose we are using a parametric approach where the components are modeled with a Maxwellian for the thermal distribution, an epithermal continuous using this function that you can find in literature, and this function allows you to produce an increasing slope in the epithermal continuous, a decreasing slope, a constant slope. It should allow you to put some cut in upper and lower energy. And for the fast neutron component, for example, a Watt distribution where two parameters are alpha and beta. So suppose to do that and to achieve, as the previous presenter showed, some result. You can see that the thermal and epithermal part are very close to those of the reference solution. There are deviations in the fast neutron component because the alpha and beta double parameter of this parameterization doesn't allow to include such a spectrum broadening, which is due to the physical interaction, to the nuclear reaction, inelastic reaction occurring in the iron. So there should be a warning prior to this, to the usage of this parametric approach. Okay, my parametric approach, I tested my parametric approach perhaps in the past with sources that are like Californium, that are like americium beryllium. But what happens when these sources are altered by inelastic reactions? This is a question that the user should think, before choosing an approach or another approach. Okay, but possibly the solution that the parametric approach is proposing you, that is this higher peak in the fast domain, provide as good folded count as the green solution, the reference one. So from the mathematical point of view, possibly the two solutions are providing simulated counts or folded counts that are similarly matching the reference count. But the point is there are some physical aspects that should guide our process toward a more realistic result. Another approach could be, okay, I have in mind that possibly the inelastic reaction taking place there are leading to some deviation or deformation in the spectrum, so I will look in literature if I can find something that can be used as a reasonable guess. And then I will apply an unfolding code or unfolding method that doesn't rely on parameterization of the spectrum, but on altering some gas spectrum using some convergence rule. In this case, I tried to do something I didn't make a simulation of the radiation room but I took a literature example and I tried to alter this high energy part just to see what will happen with unfolding. So this literature high energy spectrum that in some way is taking into account the formation or degradation due to interaction with high atomic number material is certainly not exactly identical to what we expect the reference solution, but we will see what happened with the code. Then I tried to assemble a reasonable gas spectrum by putting this literature spectrum. Then I put a generic thermal distribution with temperature coherent with the room temperature, and then I put a flat continuous. Okay, I made the sum of these three components without taking care of the proportion, because with some experience in unfolding, we realized that unfolding process cannot add structure that are not included in the gas. If this happens, is a warning signal that possibly something wrong happened. But unfolding can correct the proportion and the shapes of existing structure to guide the gas toward a solution. What happened? We have here the reference spectrum, the green one. We have the gas spectrum, the black one. The black one is the one I assembled by eye, by simply summing a thermal distribution, an epithermal flat, and a literature degraded spectrum of an americium beryllium from high atomic number attenuators. So you see that the result of the unfolding is the red one. You see that the unfolding is able to change the shape of the spectrum here, where I intentionally added fluence in the beams above 1 MeV, is also able to correct the proportion and to provide a realistic or reasonably realistic epithermal domain, and to correctly fix the height of the thermal distribution. This is one step of, I would say, step one of preparing a kind of pre-information with some reasonable hypothesis, but not taking too long and without taking too much effort. Another approach could be, well, I made a parametric analysis, and the parametric analysis, which is usually good for thermal and epithermal components, tells me that the thermal plus epithermal account for 66% of the fluence. This was the result from the first example, the parametric example. Then I will add this literature spectrum with the weighting factor 34% and try to make some continuous, try to match the spectra here where the spectra are linking, in order not to produce discontinuities in the gas spectrum. Gas spectrum should not offer discontinuities, otherwise the unfolding code will enhance these discontinuities, producing possibly errors. So if we try to use this educated gas spectrum, educated why? Because before this educated gas spectrum, there is a parametric analysis producing thermal and epithermal parts, and because there is a literature study producing some realistic spectrum for the fast energy component, that is the one that undergoes the degradation due to the ionosphere. So look at the result. So again, the unfolding tends to place shapes and proportion in the right mode. Again, the unfolding is able to reduce this high energy component, and again, a good reasonable shape for the epithermal and the right height for the thermal. So I try to show you what would possibly be the results of an unfolding process, applying 3 different levels of pre-information preparation and unfolding approach. So after unfolding, after you get a spectrum, as Carlos correctly said, plot the spectrum. Are there negative fluence? This can be a problem. This is a problem. Is there any double thermal peak? Is there any thermal peak shifted to unrealistic energies? These are error signals. Okay, suppose the spectrum shows some meaningful shape. Try to fold the response matrix with the resulting spectrum and compare the so-called folded counts with the reference sphere counts. If you see some important deviation compared with the budget, uncertainty budget, this should be a warning signal for the user that the process could have been affected by systematic effects, biasing sources. But suppose there are no such systematic problem and that you observe a kind of compatibility of the folded count with the reference count. This is certainly a necessary condition, but it doesn't guarantee itself the correctness of the spectrum because, as we say, we the three of us said, unfolding is an underdetermined problem, so you can have infinite results, infinite spectra satisfying the counts. Some recommendation, possibly if you use some I would say unrealistic guess like the flat in lethargy, a flat in lethargy spectrum, possibly the folded count that you get in the end by folding your resulting spectrum with the response matrix are coherent with the experimental counts, but the shape of the spectrum will warn you that this is not a good gas spectrum to start with. It is unlikely that when starting from a flat in lethargy spectrum, you obtain a very accurate final result. And also, as Carlos said, Bonner spheres are a good fluence monitor. So it is likely that even if the shape of the spectrum is not correct, the fluence is correctly estimated, but not the ambient dose equivalent, because ambient dose equivalent conversion coefficient heavily depend on the energy distribution. So another check that the user should do is compare the result with literature data or papers from similar scenarios. So I will conclude. Application of unfolding code needs some experience that you can gain through training courses, comparison exercise. The unfolding task always include a certain degree of complexity, difficulty. We saw this because significant fraction of deviating results were observed even in simple scenarios. So preparing reliable pre-information is crucial. And even if you use a very well-known code and validated code, if you feed the code with the deviating guess information, the result could be wrong or deviating. The user of the unfolding code should have sufficient physical knowledge to judge the radiation environment and then to make significant hypotheses on the pre-information to be used. Should have minimal mathematical computational tool to translate this physical knowledge into a priori information adapted to the specific code, and should have sufficient experience to currently judge the result for plausibility and accuracy. So I thank you very much for your attention. And I give back the word to Jose Maria.
Thank you very much, Roberto. I think there's one last slide. Okay. As you maybe after these short, not lectures, but presentations, I think one of the concept of the thing that probably you realized, if not know before, is that neutron unfolding is not a simple problem. So 1 hour is not enough to learn about unfolding. So there has been, or there is one course organized by EURADOS in collaboration with PSI and PTV on neutron unfolding that will take place in July, and it is a course of 4 days. Unfortunately, this course is busy, so there is not possible to register for more participants. But the idea to put this announcement is for 2 reasons. First one is because you can register, and if there are some vacancies because some people is not able to attend, well, you can be admitted for this course. This is one thing. The second thing is that you can register, and if there are some people interested in this topic, obviously EURADOS will consider the possibility to organize another course of unfolding of wonder sphere spectrometer for the next year or whatever. This depends on how many people could be interested in this topic. But I think this is very important to keep in mind, that the idea of this webinar has been to summarize these things about the exercise, but obviously 1 hour, you can see it's not, the purpose was not to teach deeply how to deal with the unfolding problem. Now we can have some time for some questions. You can make the questions on the question and answer section on the right. We already answered a couple of questions. Here I have one. Maybe I don't know if maybe one possibility, instead of just writing the answer, maybe could be faster if some of us reply or answer by voice. I don't know if this is okay, but probably it will be faster, that we can speak faster than writing. I think all of Roberto and Carlos and myself can read the question, and this one is about from Mara Georgiania, that say that she have a bonded sphere system in the laboratory and we intend to start. Yeah, it's perhaps, I don't know if Roberto or Carlos can answer this question.
Yeah, just okay. I think that Mara is having the problems that everybody who's starting with spectrometry bonded spheres has, is that where to look for information. So to my knowledge, there is not a single relevant source of information to be seen, or I mean, I am not able to give a single source of information for that. So maybe we have to make, all of us, an effort to put together also information on the exercises, on the unfolding courses, and so on. Maybe this question was made before the announcement of the unfolding course, I don't know. So one of the places where to look for is look for unfolding courses. It's probably much more useful than trying to find several papers or several booklets where partial information is given about different unfolding possibilities and codes. I don't know, Roberto, if you have something else to add to this question. To my knowledge, there is not a single source.
Yes, I agree with you. What we could do is to collect material and make a list of references that can be relevant, even for different unfolding methods, and send and make this list at least for starting a tentative list of material that can be made available to EURADOS and then spread to the participants. For starting with.
Want to comment something, Jose Maria, about the questions already answered before? I mean, the difficulties of the information to handle. Okay, Jose Maria has already answered that putting together a lot of information has been complicated, and as he says in his answer, in his written answer, one of the most complicated things was to try to find where the source of the discrepancies that we were finding were. In the sense that sometimes not all the information provided by the participants was clear. We found out that there were many mistakes on normalization of the fluids. We were asking for, as far as I remember, in the data sheet that we were distributing, we were asking for unit spectra. And when we made the calculation with the spectra that the participants sent, most of them, the integral was not 1. So we had to check all of that, renormalize, and then try to find discrepancies or mistakes where in some cases could even have been cut and paste mistakes from the Excel files, or even format conversion mistakes. I mean, the data were asked in an Excel spreadsheet, and at that moment we were not that aware that in some countries the Excel worked with decimal separators, points, and in some other countries it was with decimal separator, commas. When we import one of the files to another different Excel version, it makes a complete mess with the numbers. So we had even to cope with that just before starting to understand the unfolding results themselves. So there are many practical problems which are unsuspected before starting the exercises, that you have to cope with them, and sometimes it has not been so easy.
Concerning this question, just a final one more comment about the source of information. If I remember correctly, I need to check. There are many papers that have been published about unfolding with Bonner spheres, but in particular there are some not exactly review, but in some monograph published in radiation protection dosimetry or nuclear instruments and methods, I think there are some review papers that can be used as perhaps as a starting point. I indicated now in the Q&A section the email address of Carles, Roberto, and myself. So one thing that I can do is just to look for this list of references that can be useful for this question. And if some of you send me your email, I can send you this list of references that perhaps can be useful for you. So please feel free to send me your email, and I will send you this information. And also, please, if you have some question that perhaps it's too complex or you prefer to ask later by email, there's not a problem to send it. Okay, I see here the question, the comments by Mara Georgiania. I thank you to you for your interest, and we will try to provide you this information about relevant material. The question is that there are, if you look for in some database about references on this topic, you can find hundreds. So sometimes the key question is to find 3 or 4 that could be particularly relevant. In this case, to prepare the 2 papers we published, we made some filtering. So, well, one of the things you can also do is the second paper we mentioned that it's open source. In the references, there are some paper cited that describe, or in particular, the main questions about the unfolding problem applied to bonus sphere spectrometry. But anyway, if you send me your email, I will send you and any other the information about that. There is also one question, by Andreas Simbo, is look as if the effect of a sphere can disturb the field is bigger for a smaller sphere than the bigger one. Well, this is not well, actually not for a smaller sphere. This is something I presented, and actually it was more significant for the intermediate sphere. I analyzed this with Monte Carlo simulation because this is more my field. I'm not expert in unfolding, and what I found is that smaller spheres don't perturbate the field. And obviously, the biggest sphere perturbates significantly the field. But this perturbation affects mainly to the thermal neutrons. And thermal neutrons are not measured by bigger ones. So the effect was more significant in the intermediate sphere, because these intermediate spheres were bigger enough to perturbate the field, but not so big that to be insensitive to the thermal one. We made this simulation in the first paper I mentioned it, and I think it's described in this paper. It is also say in the answer by Wick, in the second answer by Wick Tanner. Yes, thank you, Rick. The booklet for the problem specification can be provided also for training purposes. All this exercise is also available in as complementary material or supplementary material in the second paper. So if you enter in the second paper, which has been published in radiation measurement, you can download all the information about this exercise. And our idea is to put all of them also in the EURADOS website. Probably will be available in the EURADOS website within the next days. Because one of the intentions with this exercise, obviously, well, the intention is not to say what solution is good or what is not good and so on. No, the purpose is to help or to assist people to train themselves in the use of unfolding problem. So this information is available, most of them in the second paper as supplementary material, and will be also available in the EURADOS website just shortly, within the coming days.
Jose Maria, just let me add one thing. Maybe it is good for working group 6 in EURADOS to finalize these tasks. I mean, the intercomparison exercise, just by setting up a list of references for the people who want to start working with that. I don't know. I think this is, as you said, the work is mainly done with the publication, with the last paper published. So maybe just collecting that and having that available in the EURADOS website could be a good solution.
I think this is something that we can prepare and could be a good way to close this exercise, and we can put all of them in the EURADOS website together with this comparison exercise, and in the same way as it has been done for all other exercise organizers. Yeah, it's what this is. This comment by Rick Tanner is continue with the discussion or the question that was said before by Andrea Simba. Is actually this ping pong effect. It's we call it ping pong because when we put the sphere close to a wall, this ping pong effect means that some neutrons that without the sphere directly interact with the wall. When the sphere is close to the wall, there could be something like that. So it's like a ping pong ball, and this is this perturbation. Well, actually will affect the more significantly the intermediate sphere. This is something that we quantify doing the Monte Carlo simulation, but it is we think that it is also understandable from a qualitative point of view because of the reason we mentioned before. I don't know if you have more questions. Otherwise, maybe now it's 20 minutes past 4. I will say, but I think this is it's in the chat. Someone that is a full member of Working Group 6 that he say that he currently using FITS code. Using FITS code and any quick calculation with FITS. And, well, then the upcoming. I'm not sure to understand the question. Because in principle, there is not, this result has been already published. So the only thing we are talking about that is not about doing some additional publication, but just to put in the EURADOS website a list of references that can be useful for people starting with unfolding. Maybe we didn't explain it clearly. But in this moment, we are not planning to do new publications about this exercise. Yeah, not in this moment. In principle, no, it's not the case. Thank you. So I think, well, in the Q&A section, I put some questions before the emails of the three presenters. In our case, if you have a look on the paper, you can find also the emails of or our emails. So if later you have some other questions, please feel free to send an email to us, and we will try to answer as the best we can. So otherwise, I think it's 1 hour and a half. I think this is a good duration for a webinar. And well, we hope all this material from the exercise that it is available in radiation measurement will be also available in the EURADOS website shortly, within the coming days. I don't know if maybe the organizers or someone want to say something just to close the webinar, or otherwise I think we can close it now. Just perhaps the host